right. So I am recording this lecture from this point forward. Most people seem to be keeping their mics quiet anyway, but I'm recording this window here, so it's me and what I'm writing here, and then my microphone. So I'm not going to record, the chat conversation or the list of participants or things like that. If you want to use your microphone and you don't want your voice recorded, send me a chat message and say, hey, can you turn off the mic? And I'll do that. And you can talk without being recorded. But I'm doing this not as a substitute for coming to class, but to try to make this stuff that I'm writing here available offline. So I'm going to start recording these lectures, and I will post a link on Canvas to where you can get them. So rather than furiously writing and trying to copy down everything that I write, you can spend more of your time hopefully thinking about what we're talking about and writing down the highlights. But you can go back and get that. So I was planning to do this starting today, and I forgot in the beginning of class because it was so hectic. But my plan for now going forward is to be recording this part of the lecture, just the stuff I'm writing down. So that will be available. And if you have any concerns about that, let me know. But like I say, I'm just recording that part of the presentation, so it shouldn't affect anybody negatively. But let me know if you've got any concerns about it. All right. So that's the idea of a function. So some definitions. Throughout this course, we're going to talk about a concept, and then we're going to end up with a bunch of definitions. So if I say something like, yeah, I'm going to keep doing this in person also. So this will be available going forward. Let's see, to be clear, we can't do f z to z, f of x equals square root of x. Square root is funny. So so someone asked about the square root of x. So if we say like f z to z, well, we can't do that because we can't take the square root of -1, for example, right? But if I went from z plus, which is the set of positive integers, I can define this function, but the number 2, the square root is not an element of z, so that wouldn't work either. But if I went from, say, the positive reals to the set of reals, I could define a square root that is a well-defined function, as long as I agree that the square root of 9 is positive 3. And in some ways of looking at it, the square root function has two possible values. The square root of 9 could be positive or negative 3. But if I did something like this, absolute value square root of x, now that's a nice, well-defined function. So this is a timely question. Yeah, if I went to the complex numbers, then I would be one of the possible values we could assign, and so the square root of -1 would just go to I. And so that's a perfect question for what I was leading into, which is that when we talk about functions, we have to pay a lot of attention to what these sets actually are. And a lot of times we get, carried away with, well, let's define this function. What does it do? What's the lines of code? What's the mathematics and so on? But we really need to pay a lot of attention to these sets themselves. And so this set, A, the set of things we are mapping from, this is called the domain. And the set of things we're mapping into is called the codomain. And so we need to know what those two things are, domain and codomain. And if A is an element of set A, f of A is called the image of A. So this is the thing that we get when we take little a and we say, what is it mapped to? Sometimes we just call that the image. And then if we look at the set of all f of a such that a is in the set big A, so the set of all the things that get mapped to, this is called the range of the function. So this is the domain of f, this is the codomain of f, and this is the range of f. Alright, so examples work better sometimes. Let's have f go from the set of integers to the set of integers. F of x equals 2 times x. Alright, so what is the domain of our function? It's a set of integers, good. What's the codomain of the function? Set of integers, alright. What is the range of the function? Yeah, the set of even integers, right? Even though 3 is an integer, it's part of this set, there's no element of the integers such that f of that element is equal to 3. In other words, there's no thing in here that maps to 3. So the range is actually just the set of even integers. And the range can be a proper subset of the codomain, or it could be the entire codomain. So what if f of x equals x plus 1? Same domain and same codomain. What's the range of this function? F of x equals x plus 1. So that's also going to be the set of all integers. Right? It's not just the odds, because f of 3 is equal to 4. So the number 3 maps to 4. Right? So the domain and codomain are z. That you can just read from the way the function is written. But the range in this case is all integers. Because any integer you think of, I can find some x so that x plus 1 is equal to that integer. Is that making sense? Cool. Alright, what about f of x equals x squared? Same domain and codomain of z, but in this case the range is more restricted, right? So what's the range look like? Yeah, the square numbers, so 0, 1, 4, 9, 16, and so on. And yeah, in particular, none of those are negative. Alright, cool. So we could have, you know, something like this. We could have a function f going from the set of all integers to the set 0, 1. Well, let's make it even weirder. Let's go to the set of smiley face and sad face. And we could define this function as follows. F of x equals smiley face if x is even, sad face if x is odd. Is that a valid function? Yeah, absolutely. So in this case, the domain of the function is the set of all integers. The codomain of the function is a set consisting of a happy face and a sad face. So the codomain we usually don't even talk about. It's just the thing that we say the function maps into. But it might be bigger than all the possible values, right? For example, here, f of x equals x squared. Since I said f goes from z to z, z is technically the codomain. But the range, the actual values in there that we can map to is, in this case, just the set 0, 1, 4, 9, 16, and so on. So codomain is just, what we write here on the other side of the arrow. It's usually not very interesting. The domain is very interesting, and the range is very interesting, though. So yeah, there's a function. Alright, so two functions. Let's have two functions a and b, or f and g, with the same domain and codomain. So two functions f and g are equal. And we can write f equals g if and only if f of a equals g of a for each element in the set A. So two functions are equal if and only if they agree everywhere in the domain. Yes, you got it, Eric. There can be two things in the codomain that cannot be outputs from the function, but every function output will be in the codomain. Awesome. Alright, so we can define functions themselves as being equal. It means they're equal everywhere. And it's kind of what you would expect, right? If you drew their graphs, if you could do such a thing, they would be exactly the same graphs. We can also compose functions. Suppose f goes from a to b, and g goes from b to c. We could do something like take an element A, map it through f to something in b, and then map that element in b through g to something in c. This is called composition. And we probably won't get into that a whole lot, but this is like a nested function call. It's like inside your function f, you call a function g. All right, so we'll make a few comments on that. Give an example of equal functions. Yeah. I mean, this is kind of a silly example. Right? I mean, we have this thing called algebra that, you know, we could take this and expand it and find out that this expression is equal to x squared. But if we didn't know algebra and we were just given this function and we were given that function, we could, you know, evaluate this at every integer and evaluate this at every integer, and we'd see they were exactly the same, and so we could say, okay, f is equal to g. What algebra, right, math 110, 111 does for us is it lets us, you know, symbolically manipulate this and reduce it down to that. And it gives us this insight that, oh, if we were to plug any number into here and plug the same number into here, we'll get the same thing out. These functions are equal. That is a phenomenally advanced concept if you're living in ancient Rome, by the way. Algebra was something that eluded Europeans for hundreds of years, while countries in the Middle East were developing algebraic systems, and the European world was, you know, floundering in the Dark Ages. So this is, you know, almost too obvious to actually write, but it's actually a fairly profound notion to be able to say that these two things are the same, that they agree at every possible value. The fact that we can see that by just multiplying this out, subtracting 2x1, getting x squared, is actually a pretty powerful result. All right, so let's shift gears a little, and let's talk about sequences. So with sequences, we are talking about things that have orders. So a sequence is something like, you know, the sequence of integers 1, 2, 3, 4, 5. Or the sequence of integers 1, 2, 4, 8, 16, dot, dot, dot. Where each number in the sequence is twice the previous number. So this is a finite sequence. This is an infinite sequence. So sequence is an ordered collection of things. Here's another infinite sequence, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so on. It's not a set, right? So the fact that we keep coming back to the number 1, that's not a problem, right? Here's another infinite sequence, 1, 0, 1, 0, 1, 0, 1, 0. It's just an ordered collection of elements of a set. So we can actually think of a sequence is a function from a subset of the integers to some set S. So here's an example of a sequence. Triangle, comma, square, comma, 5-sided thing, comma, 6-sided thing, and so on, right? I could have a sequence of polygons with an increasing number of sides. And I could define this sequence, you know, by doing this with dot, 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 and commas, but I could also say, you know, f goes from the set of integers, starting with 3, to the set of polygons. And I could say f of x equals an x-sided polygon. So f of 3 is just a 3-sided shape, f of 4 is a 4-sided shape, f of 5 is a 5-sided shape. And my sequence I get by basically writing f of 3, f of 4, f of 5, f of 6, and so on. So we can define these somewhat formally, but informally, just think of it as, you know, a sequence of things, right? Sequence meaning they're ordered. So there's the first thing, second thing, third thing, and so on. And so we write a subscript n for the nth term in the sequence. So for example, we could have a sequence of real numbers, 1, 1/2, 1/3, 1/4, 1/5, and so on forever. And we could write an equation for that. The nth term of the sequence is just 1 over n. And we could say n equals 1, 2, 3, 4, and so on. Or we could write a sequence where a n is equal to, 5 times 2 to the nth. So in this case, our sequence, well, if n is 1, 5 times 2 to the first would be 10. If n is 2, 5 times 2 squared would be 20. If n is 3, 5 times 2 cubed would be 40. 5 times 2 to the fourth, and so on. So we can define a lot of different sequences. All right. The reason we're interested in sequences is because of something called a recurrence relation. And so this is a pretty major concept that we'll talk about a lot. So a recurrence relation for a sequence for example, a1, a2, a3, dot, 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 is an expression for the nth term in terms of a1, a2 up through an minus 1. A recurrence relation for a sequence is an expression for writing any term of that sequence as some combination function something of the earlier terms. So for example, I had a sequence here, 10, 20, 40, 80, and so on, right? This was the first term, the second term, the third term, the fourth term. Is there a way to describe the fifth term as some property related to these earlier terms? Yeah, it's just 2 times the fourth term. And, you know, the fourth term was just 2 times the third term, and the third time was 2 times the second term. So a recurrence relation for this might be the nth term equals 2 times the n minus first term. Yeah, I think I'm probably overcomplicating it if it's feeling that way. We can think of it, a sequence, as just a set of these things, but I'm adding a little bit of extra machinery here that we'll lean on in a bit. But yeah, if it's feeling overly complex, back it off a little and just think of it as a sequence of things. So recurrence relation is a way to describe an nth term as some property of the earlier terms. And when we have a recurrence relation, right, we could say, okay, what's A5? Well, it's twice A4. Cool. What's A4? Well, it's twice A3. Okay, thanks. What is A3? It's twice A2. Okay. What is A2? It's 2 times A1. But if you say, what is A1? And it's 2 times A0, well, there is no A0 here, right? I said our sequence starts with A1. So we also need sometimes what's called an initial condition. And the initial condition is where we actually state the value of one or more elements of the sequence. So in this case, our initial condition might be A1 equals 10. And this would be the recurrence relation. So the recurrence relation is AN is twice AN minus 1. The initial condition is A1 equals 10. Alright, what we've got here is like, 30 to 40% of the entire course. And will lead to probably the most important thing I want you to take away from the course. And we're going to come back to this later. But this is our starting point. So recurrence relation. Describe the terms of a sequence in terms of earlier terms in the sequence. All right, so let's look at some other examples. So what would this sequence look like? Here's an initial condition, here's a recurrence relation. So see if you can tell me what the elements of this sequence are. The first few elements. All right, the first element is definitely 3 because it tells us right here A1 is equal to 3. What is A2 equal to? Right, this says it's just 2 plus A1. Since A1 is 3, A2 is equal to 5. The third, A3, will be equal to 2 plus A. 3 minus 1 is 2. 2 plus A2. And A2 we just discovered was 5, so A3 is equal to 7. So yeah, this is just a set of odd numbers, starting with 3. So that's all there is to this. But it turns out this is going to be a really, really important concept. What do the elements of this sequence look like? So I agree A1 equals 1. What is A2 equal to? So someone tell me just what A2 is. Right? A2 is just 2 times A1, which is going to be 2. Alright, so what about A3? There we go. Alright, so A3 is going to be 3 times A2, which is going to be 6. And then A4 will be 4 times A3. Since A3 is 6, 4 times A3 is 24. So what are these things? You know the name for them? Yeah, these are factorials. Perfect. So this is a recurrence relation for factorials. It's got this relationship and it's got this initial condition. This was a recurrence relation for odd integers, 3 and bigger. All right, let's say you have, you go back in time to when banks actually paid you to loan them your money with something called interest. And let's say a bank is giving you 7% annual interest. This happened when I was a kid. You could put $10 in the bank and you'd get 70 cents back after a year, which was a great return. Okay, so let's suppose that you put $1,000 into your bank account. And you come back 1 year later and you want to know how much money do we have. This is simple interest. Thank you. You come back 1 year later and you want to know how much money do you have in your account. And the idea is you're going to have all of your original money, assuming no one robbed the bank, plus your original money times 0.07. It's 1,070 big ones. Alright, so you decide, well, that's pretty good, that's easier than working, let's do that another year. So you come back 1 year later, and you're going to have all the money that you had a year ago, which is P1, plus 7% more of what you had at the beginning of the year, which is whatever that turns out to be. A little bit more money. But this is actually equal to so instead of 1,000 here I can put P0. Right, this is actually equal to let's do a little bit of algebra here, right? And say this is P1 times 1.07. And this is actually P0 times 1.07. Because that's P0 times 1, that's P0 times 0.07. Well, it's compounded annually. Whereas actual compound interest is compounded instantaneously. That's a whole different topic. But, so after year 2, we have 1.07 times what we had in year 1. But what we had in year 1 was 1.07 times what we had in year 0. So this is actually P1 is P0 times 1.07. times 1.07 equals P0 times 1.07 squared. And then if you come back a year later, you're going to have all the money you had at the beginning plus 7% of what you had in the beginning. And if you do the algebra, this turns out to be P0 1.07 cubed. And so you can extrapolate from this and find that after n years, what you have in your bank account is your initial balance multiplied by 1.07 to the n, where n is the number of years. So that's a basic formula for compound interest. And again, it's a recurrence relation, right? Your balance at the point n years can be described by this relationship, you know, in terms of P0. But you also need to know this initial condition. What was P0? Because we can't find P0 by using this formula. But if your initial balance was $100, right, then your balance at time n is 100 times 1.07 to the n. All right, so that's the first intro to recurrence relations, and we're going to talk about them a lot throughout this course. So Wednesday, I will talk really briefly, like 5 minutes max, about matrices, just so that we can say we talked about matrices in here. And then we're going to start talking about the next unit for the course, which is propositional logic. So we'll pick up from there on Wednesday. All right, that's all I got for today. Homework due Wednesday, yes. What does the bar P symbol mean from... probably positive integers, if that's a P with a double bar. Yeah. All right, cool. Have a good one. I will catch everybody next time. I'll post an announcement to make sure that we're in person, but I'll let you know tomorrow.